Purpose today is to find acceleration and position of a particle in motion. Okay, so we will derive acceleration of particle equation, and then how incompressible and compressible affects acceleration of a particle, motion of a fluid particle, meaning the position itself, the motion, and then we will do some simple question. So we should start today. So I'll take this opportunity to say that it will be an introduction. So I'll just talk about a few things and then we'll just call it a day and then we'll do some derivation later, I think, if I have time. So yeah. So this is a so imagine you have a particle, okay, drawn in this black color zone over here. Okay. So this black particle is being bounded by this rectangular shape over here, as you can see. If the v, w, and u are velocity vectors, okay, so now we are talking about velocity, we are not talking about position, we are talking about velocity, and the velocity itself move in x direction, y direction, or z direction. It all depends on how you want to move, right? So you have a fluid flow, okay, in this direction. Suddenly there will be a certain velocity that pushes this certain small particle in from here to here and from here to here, right? So there will be a velocity of the particle, okay. So what are we trying to find it out? So how do we derive what I've told you about acceleration? So they actually use thermodynamics, the first law, the conservation of energy, where the mass flow of the volume, okay, the mass about flow out over here, minus the mass flow into the volume, okay, is equals to the net change of mass flow inside the volume. Okay, so we'll be taking this concept. It's a very abstract concept, but in terms of equations, we're talking about the mass flow, the time, and so on and so forth, especially velocity. So if you were to zoom in and do my equation over here, okay, so what is this? So this is actually this in terms of coordinate system now, okay. So we imagine we call this point, okay, let me write it down. Let's do this. So let's call this point, okay, we call this P with a certain coordinates x, y, and z, right? So this point is considered x, y, and z, okay. And maybe if you are keen that maybe what is the point over here, okay. So this point over here is actually P instead of x, okay, instead of x is actually x plus dx over 2. Okay, later I'll explain why. And then the y and z didn't change, right? There is no direction in terms of w and v, right? So y and z, okay. So therefore, at this point is this, and at this point is actually p x minus dx over 2 y z, since there will be no y direction and then z direction movement, okay. So what is all this mean? Okay, so what is dx? Dx is actually this parameter over here. Maybe I should draw it in green. So this is dx. This whole piece is dx. We're talking about dx, and then dx over 2 is simply saying we're taking reference from this point. This is x. X minus dx over 2 is actually this point. Dx, x plus dx over 2 is actually this point, right? So I hope you get what I mean. So x itself is at this point. So dx divided by 2, it's somewhere here or somewhere here. Taking in consideration that y and z is constant. So from here you can actually straight away know that we're actually analyzing things in terms of x direction. If you can see, you're curious of how the this particle move. Is it 2D, 3D, or what? So to create an equation that can describe 2D, 3D, we actually analyze in terms of 1D first. So we actually analyze the x direction, which is the u, okay, in this case. So this is what we are talking about all the while. And what is the difference between this and this? Okay, they're actually the same. It's just that it's being drawn in such a way that it's pretty much tough to understand. So let me identify. So this is P x, y, z, which is over here. Same thing. And then this is the point. over here. Okay, this is the point we're talking about. And then as you can see, identified is over here. This is x minus dx over 2, while y and z are the same. Okay, and y is the left and right. Okay, this is just this point. This piece is actually left, and this piece is actually right. You have a particle flow, okay, with a certain velocity u. Okay, as I earlier mentioned that w, v, and u are actually velocity. Okay, they are velocity. They are not coordinates. They are velocity. So u comes in, and at this point u comes out. Okay, u comes out with a certain velocity. Okay, so with this we'll explain how this is being derived, and then the rest should be quite easy to talk about. So we shall hold on. Alright. So in order to find the velocity that is coming out from R, okay, on surface R, okay, we are trying to find out using a certain rules, okay, in this case it's Taylor series. And how do we change this into this? And what is actually the meaning of this, and what is the meaning of this? I'll just explain over here. So as you can see, the velocity of u and x, okay, at this point, okay, let's take, because it's a little, yeah, but anyway, so at this point it's actually u x minus dx over 2. Okay, and then y and z we take a constant, so we don't put it like that, right? So this is the velocity at this point, this is the velocity at this point, ux. So in fact this ux is actually this point instead of this. Okay, so x plus, if it's x plus dx over 2, is we are talking about the velocity at this point, right? So in this case we'll talk about ux plus u dx divided by 2, right? The velocity at x plus the velocity the velocity within this spectrum of, I mean this range over here, right? So this is just a set of notation that you should actually go and check it out. Let me repeat again. Okay, u dx over 2. Okay, okay, let me repeat again. So previously I say that the velocity of ux is actually this point, while the velocity of at this point is actually ux plus u dx plus 2. Okay, while this thing describes the this range, however, it is not it does not describe the quantity of velocity, but rather that it describes the position at this point. Okay, u dx divided by 2. Okay, because your datum reference is over here, ux, right? So when you ux plus u dx plus 2, you're taking a position over here. I mean, you're taking the velocity position over here. So in other words, we are just simply describing this point in terms of velocity. Okay, so this is the equation that we're talking about. Okay, maybe I should write it in a more clearer way. So this is our subscripts. So the velocity over here and the velocity over here is totally different. Okay, this may be slower than this. Okay, so just to let you know in a more precise way. And then is equals to u plus dx over 2 partial u partial x. How do you derive this? Okay, so let's say we have this as fx is equals to this. Fx naught is actually the position over here. Okay, so in fact it's actually u x, okay, plus, okay, so we are talking about u, you are describing this thing in terms of this point plus this point, right, plus your velocity across this system. So therefore this ux stays the same because this is the main thing. This stays the same. Okay, while there is no change in u dx over 2, so therefore we skip it out, plus the differentiation of f prime x naught. Okay, so therefore we will have partial u x partial x, right? We'll take a derivative of this portion over here, and then multiply by x minus x naught. X minus x naught is simply ux. Okay, maybe I should say it in a more, okay, anyway, so later I'll just explain it. It's a little complicated at this part, so I may be wrong somewhat. So x minus x naught minus ux. Okay, so this portion over here is actually this one. Okay, and then this portion over here is actually x naught, where you're like x naught itself is simply saying that you're looking at this position over here, while this thing is talking about this position over here. While partial u partial x is the change of u across this dx. Okay, this x positions. Okay, so partial u partial x is simply this. So what does this whole thing mean? Okay, is that ux at this position plus whatever changes within this thing will give you the point over here. So this whole thing is simply saying that. Okay, I'll not because I can't explain it properly, so I'll just tell you in an abstract way. And nonetheless, you have a other systems. Okay, other stuff. So you're talking about plus partial 2, okay, well, partial 2 u partial x square, and then you have x naught again. Okay, divided. So this whole thing um will be divided by 2 factorial, and then this whole thing square. Okay, we call this whole thing a. Okay, so because I have no space, so this whole thing a. As you can see, this one is x minus x naught. X minus x naught square is just, so if I take this as a, then this is a square, right? So I'm just saying that in this manner, and then the rest of the thing. Now we are simply taking only the first two terms, so this is why I actually quite kind of ignore all this, because this is pretty small, as you see. So it's quite negligible unless you are trying to find a certain very accurate answer. But this should suffice with whatever stuff that we're talking about. So how do you decompose this thing into what is shown over here? Okay, as you know, ux, okay, you just, because my subscript x is just telling you that the velocity at this point, it's this thing, okay. So this is just saying this is actually u. Okay, velocity can be any velocity, but we're talking about velocity at this point, plus partial u partial x. Okay, partial u partial x. Okay, this x can be, is just simply telling you the position, the change in position, the change of this position to this position. That's the meaning. And then multiply by ux plus u dx over 2 minus ux. So you have u dx over 2, right? So it's a little different from what is shown here. So this u velocity is just saying it describes the changes across this dx over 2, right? So I think I can explain it well. So nonetheless, yeah, just multiplying dx over 2 in this case. You're multiplying the range, okay? Multiplying the across the range dx over 2. That's all we're gonna talking about. So in other words, this portion over here only tells you the range between this point and this point. That's all. Okay, between this point and this point. This portion describes this phenomenon, while this thing describes the changes across this point to this point, which is like yeah. So I'll leave you to think about it. But nonetheless, this is this explains Taylor series. Okay, although I can't explain it that well. Eventually, you have this thing over here, which is the same as this portion over here. Just leave a comment in the future if I happen to think of a good solution or explanation of this. I hope that this can give you a rather intuitive understanding on how those things are being derived. So this thing describes the changes from this point to this point, and UX is just the initial position at here plus whatever changes across this thing, which is being described over here. It's a little abstract, I understand, and it can be very blur, so I apologize. So I'll see you in the next video.